Yes, great. So I'm recording. The slides I'm going to create will be available on Leia also. Okay, so I'm going to save them and put them up on Leia. So you can take a look at those separately. And I'm recording, so you can look at it later. Okay, so let's start in section 2.1. Most of the problems in that section, I say most, should be fairly straightforward. A couple of them are a bit trickier. This is on page 125. So let's take a look at number 9, okay, which is usually what gives people a little bit more difficulty. Okay, so this is a true or false. Okay, but it tests your knowledge of the definitions of subset, proper subset, element of, and this can get a little tricky, especially if you have sets with elements which are themselves sets. That can get a little nasty. Okay, so this is a true or false question. So A is the following. We say 0, that little symbol, and that little symbol. So let's read this. Let's parse this. This claims that 0 is an element of the empty set. Hopefully this is clearly false. The empty set by definition has no elements. So that's it. Okay, so whatever you put here, this is always going to be false. There are no elements in the empty set, right? B. Empty set is an element of the set consisting of the single element 0. Okay, so this is also false, right? Because this set contains exactly one element, which is 0. And this claims that the empty set, which is not 0, is an element of this set. So this is not true, right? Let's skip a few. D, let's take a look at D. So this says that the empty set is a proper subset of the set consisting of one element 0. So again, remember that this symbol means subset and this means proper subset. So the only extra is that the sets aren't equal. Okay, so this is claiming that the empty set is a proper subset of that given set, and this is true, right? So the empty set is a subset of any set. And since that set is not the empty set, so this is indeed true. Okay. Again, if you have any questions at any time, you just jump in, let me know. Okay. Let's take a look at, that's a nastier one. Okay. So here's the claim. I have this set, and the claim is that this is a proper subset of this set, this and this, like that. So let's think about that. Let's think about this. Okay, so the claim is this. Any feelings about this one? Anyone wants to try it out and argue? Not everybody at the same time.
Well, I mean,
Yes.
I guess it seems true because the first set has one element as the empty set, and the second set has the empty set as well as something else. The first one should be a proper subset.
Absolutely, yes. So the key point, yeah, excellent. So the key point is this guy, not the other one, okay? So what does it mean that the left-hand set is a subset? Let's start with subset. They're obviously different. So if it's a subset, then it's a proper subset. So the only question is the left-hand set a subset of the right-hand set? What does that mean? Every element in the left-hand set is an element of the right-hand set. Is this true? Yes, this has one element. It is here. So this is true. Okay, but notice that this part is not relevant. This is really important. Okay, so that extra element there, I mean, it's relevant in the sense that there should be an extra element, otherwise it's not a proper subset, but the fact that it's the empty set in curly brackets is completely irrelevant with the question. Okay.
Could you re-explain the difference between a proper subset and just a subset?
Yeah. Okay. Let me switch slides here. So we take a set here like this. This means that A is a subset of B, which means every element of A is an element of B. Okay, so I guess everybody's okay with that. If I write this, it means that A is a subset of B, and A is not equal to B. So it's just an extra condition that they're not the same set. Do you see what I mean?
Okay,
I guess not.
more or less.
Okay. Let's see. Okay. Okay, here, let's take an example. B is 0, 1. Okay. Then 0, 1 is a subset of 0, 1. Right? Every element in the left-hand set is an element of the right-hand set.
Yeah.
But it's not a proper subset because they are equal. But 0, 1 proper subset, that is not good. Okay, because they're equal. However, not but let's change that. 0 is a proper subset. I mean, the set consisting only of 0 is a proper subset.
Okay, now I see.
Yeah.
Thank you.
All right. I mean, it's not it's not something very fundamental. It's just a definition. Okay, it's just an extra condition on this. It's like less or equal. You should think, right, when you say, so 3 is less or equal to 3, right? But 3, this is not true, right? 3 is not strictly less than 3. It's exactly the same. It's complete analog of this, right? Hopefully you see what I'm saying.
Yeah. With the example, I figured it out. Thank you.
Good. Okay. Excellent. All right. Let's take a look at. Let's take a look at 11. Number 11. Number 11. Okay, so again, true or false, and we have a bunch of statements. So A is the following statement: X, little x, is an element of the set consisting of the element X. Yes, I mean that is true. Okay, B, set consisting of X is a subset of the set consisting of X. Yes, every element on the left is an element on the right. So this is true. C, this is an element of this. Sorry. Right. So is this an element of that set? No, that is false. Right. X is an element of that set. That's the only element of that. On the right hand side, X is the only element. So the set consisting of X is not an element of that set. Okay.
You would remove the curly brackets on the first X. Would it be good?
Yes, that's A. Yeah. Was that your question?
Yeah.
Yeah. Okay. And related to your question, here's another one. So the set consisting of X is an element of the set consisting of the set consisting of X. This is true. Yes, exactly. So this is in there. Yes, excellent. E. Empty set is a subset of the set consisting of X. Yes, the empty set is a subset of every set. Yes, true. So empty set, subset of B for all sets B. This is always
Can we say that in this case, the empty set is also a proper subset?
Yeah, yes, absolutely. So the empty set is a proper subset of any set except the empty set. So this is the only one. Yes. Yeah. And last one is empty set element of this. That is not true, right? So that set contains one element, which is X, not the empty set. So this is false. However, I'll add this. If I wrote this, then this would be true, right? It can, I mean, it's confusing if you don't pay attention to the basics. It's really just testing. I mean, you just have to look at the definitions and what they mean. I mean, everything falls back to the notion of is an element of the whole theory. I mean, so this is the naive basic set theory, and it's been formalized. And if you ever do that, you'll see what I'm talking about. But chances are you'll never do that. I mean, I would say there's little chance that many of you are going to do that. But the formal set theory is based on one single thing, and it is this symbol here, this concept being an element of. Everything is built on that, nothing else. So you can always reduce everything to that. So if you have a question, is this set a subset of that set? It reduces to, is every element of that set an element of that set? That's always, okay? So it's mostly being careful and knowing what the definitions. That's mostly it, okay? So I would say that it's superficially confusing. I mean, it is slightly confusing, but not if you pay attention and you're careful. Okay, let me move on to number 25. Yeah, so again, I mentioned that this is chapter 2, and in the book, they do chapter 1 first. And in chapter 1, there's the whole showing you how to do mathematical proofs bit. So basically, if you follow the book, when you reach chapter 2, you're supposed to be able to do standard math proofs, which we haven't done yet, okay? So for example, if you look at number 25, the question is, this is the question 25, prove that P of A is a subset of P of B if and only if A is a subset of B. Okay, so now I haven't discussed this yet, this notion of proving a statement of the form this if and only if this. Okay, we haven't done so we'll do this. We'll discuss this kind of proof in chapter 1 soon. Okay, so all I want you to do is to think of this. So let me translate this. So I'll say argue rather than prove. Somehow the word prove or proof scares many people. It shouldn't, but I understand. But argue the following. Okay, so this is the exercise, that if A is a subset of B, then the power set of A is a subset of the power set of B. And also, if the power set of A is a subset of the power set of B, then A is a subset of B. That's what the if and only if means, basically, is you have to prove both directions. Okay, well, we'll talk about that soon. So it's two exercises, two separate exercises. The first one, I think, is pretty, I mean, I think you can believe this. The second one is where the contrapositive is very useful. I'm not sure I should talk about it at this point, but maybe I'll save that for when we do proofs. Okay, so save this for practicing proofs in chapter 1. Okay, so if you want to skip it for now, that's fine. Okay. I think for 2.1, basically all the other problems are fairly straightforward. There is number 47, the very last problem in that section, which is starred, and they're asking you to describe a procedure for listing all the subsets of a finite set. Now, I've talked about this piecewise all over the place, but if you think, so here's a comment about number 47. Here's just a comment. Think bit strings and lexicographic ordering. Okay, so I've talked about these two things separately. So when I argued that the number of subsets of a set with n elements has 2 power n elements, one of the arguments used bit strings, and where all the subsets are seen as bit strings of length n. Okay, and then I said you can also see this as numbers written in binary, and then I did an argument showing you that if you look at all the numbers from 0 to whatever, you list them in order in binary, then they're actually, if you write them on a fixed number of bits, they're actually like in alphabetical order. So that's sort of what 47 is asking you to think about. Okay. So bit strings, lexicographic ordering, that's one way of listing all subsets of a set. Okay, so just think about that. And I think if you have some idea of what I'm talking about right now, you're fine. Okay. If not, go back to these two sections or look at, I guess there's a solution to 47 in the book. Okay. And if that still doesn't work, just ask me. You can ask me anything, anytime. Okay.
What's lexicographic ordering?
Yeah. Alphabetical order.
Oh, okay.
It's just a fancy way of saying alphabetical order, right? So if you have 2 bit strings, right? Let's say I'm looking at 0. I mean, 0 is less than 1. Okay. So if I put 2, okay, let me. That's a good question. I should. Yeah. Okay. Okay, so let's say I have bit strings of length. Let's actually choose a number rather than n. Let's make it 8. Okay, so I have bit strings of length 8, and I want to compare them in the following way. So I want to say this bit string comes before this other bit string. So how do I compare them? I do exactly as an alphabetical order. So let's say they both start with 1, then I can't say anything. If they both then have a 0 like that, then I still can't say anything. And if there's still a 0 like that, I still can't say anything. There's the 1 like that. And eventually, let's say I get this, then I know that this guy, the first, so you see, this means that this is the first and the second. So 1 comes before 2, right? Just alphabetical ordering. Does that make sense? I could be more formal here, but I think this makes sense, right? So is that okay, David?
Yes.
Okay, so basically you compare symbols starting on the left, and if you look at the, if all symbols are the same, then this makes, I mean, it's the same bit string. So at some point starting on the left, there will be a bit which is different. One of them will be 0, the other one is 1. So the one with the 0 comes before the one with the 1. That's basically it. Okay. Okay. Let's take a look at 2.2, page 136. Okay. 2.2, page 136. I wanted to take a look at number 15. Oops. So this is similar, if not the same thing that I did in the slides, but since it was on slides, it was probably much harder to follow. So I'll try to do it here a bit slower. So we're asked to prove De Morgan's law. Hello? Sorry. Okay, so we want to prove De Morgan's law. Oh, this is wonderful. Yes, here we go. Where we want to show that A union B complement is equal to A complement intersect B complement. Okay. I'm going to follow the procedure that I used in the slides. I'm not sure if it was that one or the dual one that I did. You can, I don't know if you guys can hear the repair person.
A little bit, but it's fine.
Yeah. Okay. So sorry about that. Jeez. This is just so weird. Okay. All right. So I have 2 sets. I want to show that they are the same. And as I said, I think it was last week, a very, very common way of doing this is to show that one set is contained in the other and vice versa. Okay. So we're going to show, we show that it's not always necessary. And actually for this one, I think we can argue it directly, but I'm still going to do it that way. So we show that the complement of the union is a subset of, sorry, we're going to show that the complement of the union is a subset of the intersection of the complements, and the other way around, that the intersection of the complements is contained in the complement of the union. Okay, so these are 2 separate arguments. Okay, although I think in this particular case, the whole thing is very symmetric. It's not always the case, but in this case it is. But in any event, let's start with A union B complement subset A complement intersect B complement. I want to show this. I want to show this is true. Okay, so to show this, I must show that. So again, what does it mean? Subset, it means every element on the left is an element on the right. So I must show that every X, which is in here, satisfies, or X is in here. Okay, that's the definition of being a subset. So that's what I need to do. So what do? I take an element which is in the complement of the union. I write down what that means, and hopefully that will tell me that it's also in the intersection of the complements. Okay, so take some x in here. Now I have to do it for every x. I'll talk about that later, but it's not just, I mean, it's an arbitrary x. This argument has to be valid for any element that I choose in the complement of the union. So I call it x, whatever it is. What does it mean for x to be in the complement of the union? Okay, so this means that x is not in the union, right? It's the complement. So it's in the universal set, some fixed universal set, but it's outside A union B, okay? So what does it mean for x not to be in the union of two sets? It means that it is in neither, right? So this means that x is not in A and x is not in B. Hopefully everybody agrees, believes what I'm saying is the truth and not alternative facts. My dishwasher was actually full of clean dishes. They didn't tell me they were coming, so I don't know. Okay, so sorry, it's a bit distracting. Okay, so I took x, which is in the complement of the union. That means it is not in the union, which means it is neither in A nor in B. So x is not in A and x is not in B. And if you're paying a little attention to all of this, which I understand is not so easy, then maybe you can go for the kill with this little proof, because x is not in A. This means x is in the complement of A, and x not in B means x is in the complement of B. And to be in both sets means you're in the intersection. So this means x is in this, right? So that's the proof of that little piece, okay? So if x is in the complement of the union, and I just basically I open up the definition. I just write down what these things mean and follow this. So this is what mathematicians would call a trivial proof, because there's actually no argument. You just follow the definitions and that's it, okay? Now, of course, when we're starting out and doing these things, this is not so necessarily so trivial. We're not used to it, okay? But once you get a little used to it, you see that there's no trick. I don't have to figure out some problem solving or anything. It's just like basically just following the definitions and that's it, okay? For the second part, so this was the first one. The second one here, let's see, and I think it's just basically the same. Okay, so let's do this. So I want to show this. Okay, let's see. Okay, so I want to show the left-hand set is a subset of the right-hand set. So I take, again, same argument. So choose, so pick, so let x be an element of this. I want to show is that x is an element of this, right? That's what I want to conclude. So x is in the intersection, and I mean, yeah, you'll see this is just very symmetric. X is in the intersection of A complement, B complement. This means that x is in here and x is in here, right? What does it mean for x to be in the complement of A? It means it's not in A. So this means x is not in A and x is not in B. And so this implies, or means, it's equivalent, but it implies if x is not in A and it is not in B, then it is not in A union B. And x not in A union B means x is in the complement of A union B. Okay, so let's forget that you are watching this through a TV or whatever, okay, a screen. Let's just think about the what happened here. Let's assume that you've been listening to what I'm saying. Two extremes. You have absolutely no clue what I just did, okay? And the other extreme is, oh yeah, that was super easy, okay? And I would guess everybody's in between these two extremes, obviously, okay? If you have really no idea what happened, okay, I would say there are probably a few of you. Contact me as soon as possible. Okay, we need to fix this. If you, one possibility is that you don't know the definitions. If you don't know the definitions, this is impossible. Okay, you must absolutely know what everything means when it's written down. Okay, that's level 0. Okay. If you're sort of I'm not sure exactly what happened, try to go through it again and then try to do it by yourself. Okay, but basically all I did was unravel the definitions and use the fact that if to show that two sets are equal, I want to show that one is a subset of the other in both directions. That's essentially it. Okay. All right. Okay, so that was the Morgan's little argument there. I wanted, oh yeah, number 47. I don't know. I'm curious to know how many of you have already tried it. I don't want to give these things away because no, sorry, 47 is in section, yeah. 41, sorry, not 47, 41. Sorry. 41. Okay, so we're given 3 sets, okay? And we're told that, so we're given 3 sets, A, B, C are sets. And the question is this: if A plus C equals B plus C, is it true that A equals to B? Okay, let's look at this from a higher level. Let's say you read this, you say, what the hell is this plus thing? Okay, good question. That's an excellent question. You have to know what this is, otherwise you can't answer the question. Okay, so this plus thing, if you look, I think in the questions I said, it's defined, it's the symmetric difference, which is defined just before question 32. So here, this is symmetric difference. Okay, so if I take 2 sets, the symmetric difference is the following set. It is the set of all, let's not call them X, let's call them A, such that A is in X or A is in Y, but A is not in X intersect Y. Okay, so you take the elements which are in exactly one of X or Y. Okay. And the question here is, if the symmetric difference of A and C is the same as the symmetric difference of B and C, is it true that A equals to B? Okay. Let me just add something here. So remark, let's say I change that question. If A union C equals B union C, is it true that A equals to B? Hopefully this one is actually pretty easy to answer if you think a little bit about it. Okay. What would you say? Anybody wants to try that one?
I guess if B just contains elements in C, then A can be the empty set. So they don't have to be the same.
Correct. Yeah. So another way of seeing this is that if C, let's say, contains both A and B, if A and B are subsets of C, if you take the union, you just get C back. So A and B can be any subsets of C. Yeah, but that's basically what you were saying. Okay. So the answer here is no. And how do you prove that this is not always true? Is you just find an example. You create an example. So easy to find an example, or what we'd call a counterexample. Okay, so this is easy. So let's go back to the other question now. So A plus C equals B plus C. Is it true that A equals to B? You might try to find an example which shows that this is not true. If you try that, you'll have a little difficulty. It's going to be hard to find one. And if you start trying to think of why you can't find one, you might figure out that you'll never find one, because maybe it is true that A is always equal to B in this case, that you can actually cancel out the C. Okay. So this is an example of a question where you have to figure out what's going on first, where you're not told in advance, prove this, right? So you have to figure out what is actually the correct thing to prove, and then you have to prove it, okay? You have to see why this is true. Now, often figuring out why the thing is true and proving it is essentially the same. That's the key, right? So I'll leave that one for you guys, but it's an interesting problem. It's a cool problem. So you have to play with it a little bit. Okay. At least I had to. That's 41. Okay, let's move on to 2.3 functions. Yeah, this I did. It's page 152. 2.3, page 152. Number. Okay, so it's page 153, but anyway, so number 10, we were given functions. So we have functions which go from the set A, B, C, D to itself. And we have to figure out which are one-to-one. Okay, so again, if you don't know what one-to-one means, you cannot answer the question. It is impossible. Okay, so you have to know what one-to-one means. So what I'm saying here is, of course, I mean, if you're gonna do a test, you have to know all the basic definitions. If you don't know them, then it's not only a question of knowing them or not knowing them, is that if you don't know them, it means you never played with them. And if you've never played with them, then there's a small chance that you're going to figure out on the fly a new problem, how to solve it, right? So, okay, so what does it mean for a function to be one-to-one? I like to think that little picture, you don't send two elements to the same thing, okay? So what does that mean? So f is one-to-one means f of x is equal to f of y. If f of x is equal to f of y, then x is equal to y. So the only way that the outputs can be the same is if the inputs were the same, right? So you can't have f doing this, right? This is verboten. Okay, you can't have that. So no two distinct inputs can be mapped to the same thing. Okay, so let's take a look. I've got the first function f of a equals to b, f of b equals to a, f of c equals to c, f of d equals to d. The first one, yeah, so all the outputs are distinct. Okay, so a, f of a equals to b. I feel like I'm in an airplane right now. F of a equals to b, f of b equals to a, f of c equals to c, f of d equals to d. If you look at the 4 outputs of the function, b, a, c, d, they're all different. So yes, this function is 1-to-1. Okay. If you're bored, I'm sorry, I'm boring myself too. B, f of a equals to b, f of b equals to b. This is bad, right? F of a equals to b, f of b equals to b. No, right? I don't have to go further than that. I have 2 different elements being mapped to the same. C, you can spot it pretty quickly too, eh? F, the last one, f of a equals to d, and f of d equals to d. No, not 1-to-1. Okay, so it's just a question of applying the definition. Okay. Number. Oh yeah, number 15 is, I don't know if that's easy for you guys or it's hard. I would think that it is at first not easy because you might not know exactly what you're supposed to do. But so let me show you how this works. So we're given functions from the product of the integers by themselves to the integer. So f goes from z times z to z, okay? And we're asked if it is onto. Okay, so what does onto mean? It means that you're going to hit every possible integer as an output. Okay, so for every, so this means, so that's the definition of onto, for every y in, let's call it, yeah, okay, let's call it z. For every little z in big Z here, there exist x and y in, or a pair xy in z times z, such that f of xy equals to z. So every possible integer is an output of this function. You can hit everybody, okay? So every integer is an output of f. Okay? Yep.
Isn't that isn't that true because you can always do any integer times by like 1 and then, isn't it?
Yeah, it depends on the function though. So at number 15, you have 5 different functions. Oh, the times here is the product of sets, right? So this is a function which takes as input a pair of integers and outputs an integer, but we don't know what the operation is. Sorry, the function, we don't know what it does yet. But for the product, you're absolutely right. Yes, if the function, yeah. So excellent, actually, very good point. But so if the function happens to be this x times y, then yes, the answer is yes, because f of 1z will be 1 times z equals to z. So for any, if you take any z, you do 1 times that number and you'll output that number. Yes, excellent proof. Okay, but the functions here are not necessarily the product of the two x and y. You see?
Yeah.
Yeah,
Correct.
okay, great. Okay, so let's take a look. So for that function, the answer is yes, and that's exactly how you do it. And that's basically the trick for all the other functions. You have to figure out how you can find an input to output whatever you want. Okay, so let's take a look at f of, so they call them m and n, and it doesn't make any difference. F of n is by definition m plus n. Is that onto? Can you output anything you want?
I guess, yeah, because you can make one of them 0.
Exactly. So it's the same trick as for the product. It's exactly the same idea. So yes, it is onto. If you pick any number you want, just do that number plus 0 and you'll get what you want. So yes, f of z0 is z plus 0 equals to z. Bingo. I'm using this z here so that you can see the connection to the definition here. That's why I'm using this z. I could use any other letter, right? Let's do okay.
Sorry.
Yep.
How do we know? Like, how can we assume that n is 0?
Okay, good question. So look at the definition. The definition says for every z, there exists something. So I'm allowed to choose whatever I want, right? So the game is you for every possible output, I have to be able to come up with one input, but here's 2 integers that will output that given output. So I'm allowed to choose them the way I want, as long as there's one pair that is mapped to that Z, then I'm fine.
Oh, okay. I see.
Yeah. Okay.
Thank you.
So let's try B. And actually B here you'll see is related to your question. It might clarify. So here the function is f of mn equals m squared plus n squared. Is this function onto?
This one wouldn't be because you can get the negative numbers.
Exactly. So here you see the sum of squares. You think, okay, sum of squares, that's always greater or equal to 0. I'll never get a negative with that. So it is not onto. So not. Okay. So now how do I make the argument? That's exactly what we said. We said you'll never get a negative. So take z equals to -1. Then for no choice of mn, do we have m squared plus n squared equals to -1. So it's not onto, right? So if I unfortunately will have to stop soon, but let me do, actually, once you've seen these two, the other three, if you understood what I did in A and B, you should be able to do C, D, and E pretty easily. Okay, so I won't do them. Actually, because I'll just be repeating. So C, D, E, very similar. Okay. So let me jump to 57. Okay. 57 is, I mean, this is a bit more involved. Okay. So here's the question. They give you 2 real numbers, A and B, such that A is less than B. And they ask you to use the floor and or ceiling functions to express the number of integers n that are strictly between A and B. So use floor and ceiling to express the number of integers strictly between A and B. I'm not going to solve it. You actually have the answer, but trying to do it without looking at the answer, it is possible that you get an expression which is a bit different from when I solved it, I got an expression which is different from the one in the book, but they turn out to be exactly equivalent. They are both right. So this is not as difficult as the number 57 seems to indicate. It's sort of it's a medium kind of exercise, but it's cute. Okay, so it'll test your knowledge of the floor and ceiling functions. But if you look at examples, this it might help to do this problem. Okay, I'll have to stop. I just want to say one last thing. I'm going to modify the slides. So for chapter 1, I realized that I should have done a little bit on De Morgan's laws and things like that. So I will add some slides about extending or and to n inputs. And I'll talk about De Morgan's laws too. So I should have talked about that and I didn't. But so this is 1.3. This is in section 1.3. When I did the completeness, I went over quickly on the fact that you could write x1 or x2 or x3 or x4 and a whole bunch of them. And I didn't explain that very well. Actually, I didn't explain it at all. So I'm going to add some slides where I do this more properly, and a little discussion on De Morgan's laws. So you might have noticed, I should have done this. You might have noticed that or and union intersection and negation and complementation, there's something going on there. They look a lot they look alike, and yes, they do. I mean, they're sort of the same thing in disguise. So I'll add this and I'll talk about that. Okay. So sorry, I have to go. And you would think, well, general practitioner, I'll wait 45 minutes, but this guy is like, when I go to his office, is like, I have an appointment at 1:30. I get in at 1:30. He's the exception. I don't know. So I'm gonna take that call. Okay. So sorry, I have to go. I'll post all of this after my appointment. All right. Cheers. See ya.
Thank you.
Have a good
Thank
day.
you.
Thank you.
Thank you.
Thank you, sir.
Thank you.
Thank you.